A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast episode 62. In this podcast we cover topics such as engineering, AI, neuroscience, life, and other interesting topics and fascinating ideas to educate, inspire and engineer people's minds all around the world. I'm your host Joseph, and for this episode of the podcast I'm very delighted to welcome Bernat Font to my show. Dr. Bernat Font obtained his mechanical engineering degree in Aeronautical Engineering from the Universitat Politecnica de Catalunya, together with a master's degree in CFD from Cranfield University in a double degree program in 2015. Next, he started a Ph.D. program half-hosted by the University of Southampton and by A*STAR in Singapore, focused on developing a dimensionality-reduction method for turbulent homogeneous flows, graduating in September 2020. Following this, he has collaborated with Oxford University on the transfer of porous particles in channel flow. He is currently a postdoctoral researcher at the Barcelona Supercomputing Center, BSC-CNS, working on NextSim, a European project to develop a fast numerical flow solver for aerodynamic applications. In this very exciting podcast, we covered pros and cons of doing a PhD, turbulence, three-dimensional and two-dimensional turbulence, machine learning for CFD, and much more. For updates on upcoming podcasts, projects, and videos, make sure to follow me on Twitter as well as on Instagram. To join my weekly newsletter, engineeredmind.sh, where I share exclusive content, visit yusuf.substack.com. And now, ladies and gentlemen, here's my podcast with Bernat Font. Hey Bernat, welcome to my show.
Hi, thank you for inviting me.
Yeah, that's really a pleasure. Today we want to talk about turbulence and your awesome paper that you have released. But before we jump straight into the awesome stuff and turbulence in general, could you give us like a 1 or 2 minute quick bio? Who is Bernat and what do you actually do?
Okay, sure. So I'm originally from a town close to Barcelona called Vilassar de Mar, and I studied here in Catalonia Aeronautical Engineering, like my bachelor and my master's. And then I went to the UK to do an MSc in computational fluid dynamics. This was also a passion of mine when doing my undergrad. Like I could see that the only subjects I was actually enjoying were like the aerodynamics or any like heat and mass transfer, kind of everything in fluid dynamics. But so I really wanted to learn more about this. So I decided to do the MSc in CFD at Cranfield University. And just after that year, I decided to start my PhD also. So I started working with Gabriel Weymouth and Owen Tati, my supervisors in the University of Southampton that were supervising my PhD. And it was a PhD that was also like part-time in the UK and part-time in Singapore. This was also a very exciting experience for me because I also wanted to travel a bit while studying and while doing my PhD. So I spent 2 years in Southampton and then 2 more years in Singapore. And I've just recently came back to Barcelona to work on Barcelona Supercomputing Center as a postdoc here. So this is a bit like the super wrap up kind of summary of my professional life, I guess.
Yeah, that's awesome. When you're talking about the PhD, how is PhD life in general? Maybe you can talk a little bit about that as well. I think that's quite interesting.
Yeah, PhD life, well, there's a lot in that. So I guess there's like, as in anything, some advantages and disadvantages. Like things I really loved during my PhD was this kind of freedom that you are given as a researcher to more or less like just spend your time on whatever you wanted and more or less have your own schedule, your own kind of calendar. You set your own agenda somehow. And also, I really like working with my supervisors. Like we had a very good team, I think. But again, for me, this was an advantage. But I know this can also be a disadvantage because in the end, this is also about, personal relationships with your supervisors, and it might go well, it might not. And in any case, I had a very good experience myself, and this is something I really like working in the university with this team. And on the other hand, also, a PhD life can be sometimes, I guess, very stressful. Like, probably you know about these statistics where, like, mental health diseases are super correlated with postgraduate education, right? Mm-hmm. So let's say, like, in average, you are much more likely to get, let's say, anxiety or depression or whatnot if you are doing a PhD, let's say, than if you are not. So obviously, like all these things are also related to other stuff, right? Other lifestyles, but doing a PhD is definitely one of them. So you need to take into account that it can be stressful at times, it can be depressing, it can feel lonely, you can have like this, the symptom of the imposter, like you sometimes feel like you don't really know what you're doing and you feel like very bad about it, but it's just about the learning process, I guess. So, well, I personally had a very good experience and I really enjoyed it. And my PhD kind of life was also, I could also travel, not only to Singapore as these 2 years, but you can go to conferences, so you kind of get into this international atmosphere. You can meet people, very interesting people doing very cool work from other universities and so on. And all of these are things that I definitely enjoyed.
Yeah. How do you keep the balance personally between like a stressful PhD life and like a social life? How do you do that personally?
Yeah, well, like this is, I guess, a very personal approach, but I like, for example, to do a lot of sports, and I kept myself like busy doing sports as well when I was doing my PhD, still do it now. And this kind of brought me the balance I need. People can find, I guess, this balance in other places, maybe doing whatever other hobbies you like. For me also was music. I like to play music. I play the bass, and I was also in a band in the UK and in a band in Singapore when I moved there. And I don't know, just doing something that really disconnects you from your everyday work and your frustrations in your PhD and everything. Like you need to escape that somehow. So for me, that was the way to do it, I guess. Yeah. It doesn't mean that I didn't have any bad time. I also did have bad times during my PhD, as any PhD student, I guess. But this was manageable because of this other stuff.
Yeah. When you look back, what do you think was like the biggest frustration in your PhD, like during this time? Can you remember back?
Yeah. I mean, I guess there are two main things. First one is like when I really felt I couldn't do it. Like, so I was assigned a job, my PhD. Okay, you need to build a model to do whatever. We will talk about this later, okay? Mm-hmm. But I felt at some point that it was impossible. Like I could not really do it, and because of that, my PhD kind of was like, I don't know, didn't have any importance at all, because I mean, if it was not possible to do, then why would I do it? Why would I try like to spend 2 more years in my life doing something I don't believe it can be doable? But I guess we all feel at some point that there are like impossible goals. And also I had very good support from my supervisors. Like, I mean, in personal terms, like they gave me, courage when I needed. Like they gave me like the confidence in me, like they were trusting me I could do it and so on. So you need a good support behind it, like a supportive team. You can do it on your own, I guess, but this is easier if you have someone that supports you. So that was one of the crucial points where I didn't feel so good doing the PhD. And another one was just a very personal experience I had, and it's like when I moved to Singapore. So as I was saying, I love to do sports, right? So I was doing sport climbing, and I just broke my knee. In the second week, I arrived in Singapore. Mm-hmm. So I still didn't know anyone and so on. So I needed to have surgery like just 4 weeks after moving to Singapore. And this was a bit of a tough time because obviously I was like very far from home. I didn't know a lot of people there and so on. So I had to stop actually my PhD and move back to Spain to have surgery here, and then went back to Singapore. But during all these months I spent in Spain, I was like not sure what would be the future for me, like if I would pick up the PhD again or not, and so on. But anyway, spending time with the family here and some friends and disconnecting while having my surgery and so on, that was quite nice for me and gave me the strength to continue. And I think my best work during my PhD came right after this long-term disconnection from the PhD. So it was not a bad thing overall. Yeah.
Oh, that's fascinating. How is it, by the way, now that you mentioned Singapore and also Spain, how is this research different between countries? Maybe you can talk about that as well.
Yeah, I mean, it's not like the research is different. It's like how the governments administrate research, I guess.
Mm-hmm, yeah.
Like how much money do they put in every year, and how our research is seen from if you go to a job and you say, I do have a PhD in this topic, how do they value this or not, depending on the different countries. So in UK and Singapore, they do actually invest a good amount of money every year in research. And I think this is beneficial because obviously like research is like potential knowledge, right? You can create new knowledge.
Yeah.
And knowledge is information and knowledge is power. And you can, as a country, I guess, capitalize that somehow by creating a job market with patents and whatnot. So this is kind of long-term investment that I don't think maybe Spain is doing so well compared to UK and Singapore. Like if you look at charts like where they show the cumulative growth of the money that they put in every year during 10 years, I think like 2009 to 2017, Spain had a negative growth in research and development. Yeah. And then they improved a bit in 2018. Then they came positive out of that, but they were very far behind to other like big countries, like average in the EU or China or the US or whatever. Mm-hmm. So yeah, I think Spain really needs to put a bit more money on this and start evaluating a bit more researchers themselves, providing them a bit of better salaries. Another important point is that, so here I think we have a very good education system, which is subsidized by the government. So you can end up having a degree where you don't spend so much money on it because the government pays part of it. And if you cannot pay, you have some bursaries and some other stuff. But then you don't have the jobs that actually require the skills you have learned during all these years in the university. So a lot of people go away. So in the end, Spain is like putting money on people that they don't know what to do with those skills that they have acquired. And then they leave to the UK, for example. So all the investment they do in the students, they just lose it after all. So this is something that I think it should be improved here as well.
Yeah, would you advise people that want to do their PhD, should they take a shot and maybe go to Spain, spend a few semesters there, or how do you see it?
I mean, so Spain also receives EU money for projects for research. And there are some competitive positions that you can do PhD here and have a competitive salary similar to what you would have in the UK or in Singapore, as examples. But this is not so, like the offer on this is not so broad, right? There are a few positions. Only all of them come from EU funding. If you can find such position and you want to come abroad to do your PhD in Spain, that would be very good. So in my group, in Barcelona Supercomputing Center, we have a couple of PhD students, international ones, they had some EU funding and so on. So, and they are having a very good experience here in terms of, we have very good facilities, one of the big supercomputers in Europe. We have a very good team, like technically, our PI, Uriel Lempool, is very good as well. So it's a good place to do it, just that there are a few offers that are competitive compared to other countries in the EU.
Mm-hmm. Very, very exciting. Yeah, it's good that you give some tips. Maybe at the end of the podcast, you can give like your top tips on doing PhD.
Sure.
And what maybe to avoid and what to take care of. You talked about the bottlenecks during your PhD research, which involved obviously computational fluid dynamics, and turbulence is a big part of it. So what I would like to do is, not assuming that people listening to this podcast know what turbulence is or CFD, could you define in your own terms, as an expert I would call you right now, what is turbulence? In very simple terms, how would you define it?
Okay, so I think I would define it as in simple terms. Let's say you have a variable you're looking at. You have something that evolves in time, and when you look at this variable or this state that is it evolves in time and it's not going through a smooth, let's say, a smooth curve or whatever, and it starts to go up, down, it starts to go places that you wouldn't expect, and you would call that a chaotic trajectory line, something that you wouldn't expect. Mm-hmm. If you are going to try to predict the state of that measurement in 5 seconds, that's something turbulent, right? It's something that it has very difficult ways to, it has a very difficult way that you can predict it. So you cannot really expect what the next few seconds will be like because it's kind of chaotic. It's kind of not ordered. It doesn't follow patterns. So that's something I would call like turbulent. It's quite, and it's not an easy definition. Like if you read any book, they try to introduce turbulence, and they use a lot the word chaotic. And obviously, this is a bit of arbitrary. Maybe what you find chaotic, I do not find chaotic, or the other way around, right? But it's like something that's not ordered, that cannot be predicted easily, you cannot expect what it would be like in a few seconds, in a few time units, whatever.
Yeah. So when you talk about CFD, because you focused on it, so you obviously have a love for fluid mechanics and also turbulence, which is also a chaotic system, as you explained. And the PhD life also is very chaotic. Maybe this is like a parallel, where we can see parallels, like a chaotic PhD life and a chaotic system in CFD. Maybe that's why you were attracted to do maybe a PhD. Who knows?
Maybe. Chaotic lives.
Exactly. Yeah. Exactly. And with varying initial conditions, obviously. Why do you have the love for computational fluid dynamics? Where do you think it comes from?
I mean, when I was trying to, I guess, there's a bit of a weird thing that it applies somehow, but I guess I remember asking my parents when I was like doing my maybe secondary school and so on, I'd like to design planes because I like planes somehow, but just like, I like them flying, like how do they, but not from any kind of, just from it's so cool, right, to see something flying. So I would like to design things. But I don't really think it counts from there. I think it counts more from the fact that I really used to love like maths and physics during my secondary school and so on. And then I also started developing a very, like an attraction for programming when I was very young. Maybe I was 14. So I was very lucky that in my school, they were offering kind of optional programming, introductory programming lessons. So I was starting like doing like QBasic language stuff. And we were just programming very stupid things, but it was very cool for me. I really like to, tell the computer what to do in a structured, patterned way. And I don't know, then when I had to choose my degree, I was like in between kind of engineering, but also maths and computer science. So I really didn't know what to choose. And in the end, I chose Aeronautical Engineering because it had a bit of maths and physics and programming and so on. And when I was there is when I realized that the thing I liked the most was what I was saying before, all these modules related to, to fluid dynamics, heat transfer, mass transfer, and so on, like all the other stuff in aeronautical engineering that we were taught, such as, in the last years, just like commercial stuff of it. I was not really interested in that. And then I was like, okay, I think I'm more like a science guy, so I will stick to this. And I just wanted to specialize on this because it was what I enjoyed doing. Like I did all the optional projects they were suggesting in the CFD classes and so on. So I don't know, somehow I liked this mix of different disciplines that it has.
Yeah, why not the industry directly after your graduation? Why academia? More freedom?
Yeah, yes, definitely. So, I had this, I posed it this way, right? So I finished my MSc and I could either start doing a job in industry or stay in academia and do a PhD and see myself in, let's say, 4 years' time. Okay, during these 4 years, I knew that if I was moving to industry, I would start like from the lowest grade in industry. And this normally means like a lot of working hours and a small salary. And obviously it's the same, you then choose your working hours and you need to be, there are very different type of jobs, right? But I was just having in my head, like, I need to be Monday at 8:30 a.m. in the office and the boss yelling at me because the report from last Friday was whatever. So I was picturing myself like this, earning a small salary, having not freedom to do what I really like, or picturing myself as doing a PhD with probably also a small salary compared to industry, but with more freedom. And it's true that at the end of the 4 year, the salary in my industry job would have grown probably, but not in academia. But probably after finishing my PhD, I could just kind of match my industry position again if I wanted, right? So I could just jump to a more senior position in industry. And I was like, okay, then I don't mind like staying in doing a PhD. I like this subject. I will be, enjoying what I do. I will be traveling in conferences. I will be managing my own time. And if I want to go to industry, I'll go after it. I can do it after my PhD. And it's not like I will have lost 2 years of my professional career or whatever. I probably will be in a similar position anyway. So why not? And actually, I think it was the right decision. Now I have stayed in academia doing a postdoc, I guess, but I guess I could change at any point I wanted to. But so far, I'm very happy. I'm having this job I have now, the freedom, the a good team atmosphere, everything. So that's nice.
Yeah, I'm glad to hear that. Now, finally, before we jump to the great paper that you have released, because I saw it on Twitter, it's like is your pinned post actually the paper?
Yes.
Paper results with a nice GIF of the cylinder, wake in the cylinder. The paper goes something like from 3D to 2D turbulence and the wake of a cylinder, something like that.
Yeah.
Roughly speaking.
Yeah.
Why is it so important? Why did you investigate going from 3D to 2D in the first place?
Okay, because if you come to me as a someone who's designing planes and you say I want to do this simulation, but I only have 1 week because I have a client that wants me to build an aircraft in 2 weeks, so I need 1 week for simulation. So I would say, okay, I cannot do the simulation if I have to do a 3D simulation because it takes much more than that. But instead, maybe I can do a very good approximation in just a 2D simulation, right? So this is just the motivation of my work. Like, depending on the type of problem you have, like in turbulence, maybe you can reduce that problem from 3 dimensions to 2 dimensions, and then you just run a 2D simulation instead of a 3D, and that would be much, much faster. Maybe you can still get accurate results similarly to what you would have get in 3D. That's the motivation behind it.
Yeah, some people would say, okay, the vortex stretching term, like in the vorticity equation, is like always 3-dimensional. Why would you even consider doing 2D turbulence? Is it that significant, the results at the end of the day?
Yeah, so vortex stretching is this term that we have in the 3D vorticity transfer equation that is kind of the main difference from your 2D vorticity transfer equation. And then people point at this term saying like, okay, this is the term causing 3D turbulence. This is the term causing chaos in my system. All these things I cannot really predict in 5 seconds because of this, right? But maybe, so turbulence, I guess, is very chaotic and what we have discussed before, but there are some patterns you can find in this. But you know that the scales at which energy is transferred, let's say, what vortices you have energy containing structures are whatever scale, and then you know that how this energy will be transferred to smaller radius and so on. And we know more or less what is the rate of this energy, of this transfer, right? This comes from the Komorov of the dimensional analysis. So there is some order in turbulence. And we also know that, for example, depending on your Reynolds number, your viscous to convective forces, depending on the geometry that you are analyzing and so on, maybe you will have a direction of the flow that it doesn't contain like big like main gradients, like big structures that needs to be resolved. Maybe just some direction that looks more or less the same along. If you are going to walk that direction, you will find that the flow has more or less the same state, right? Mm-hmm. And then you can, of course, do and resolve all that direction and do the 3D simulation. But maybe that direction is just something that we can model because it looks very similar from one point to the other point if you just look in that direction, right? So this is a way that you can reduce your system from that 3D original problem to your 2D, just because one of the direction looks very similar if you just walk along it. So this is what you call like homogeneous turbulence. So that's something we can exploit maybe, and that's what allows us to do the dimensional reduction.
Mm-hmm. Why did you investigate a cylinder in particular, the wake of a cylinder?
Well, it's kind of a canonical test case for turbulence, and like this is one of everyone doing like fluid dynamics has at some point simulated like this, and obviously it has a turbulent part of the flow, which is the wake at high Reynolds regimes, and it also has a direction, just one, in which you have this kind of similarity, this homogeneity. So this was kind of a good test case for this because we have turbulence. Everyone knows what this test case is. We have one homogeneous direction, and there are a lot of experimental and numerical data you can validate against. So it's just a good test case. But you can also pick other test cases. You could pick also an airfoil maybe. This is something that I really wanted to look at, but I didn't have time to do it after my PhD. Maybe we'll do it in the future, but we'll see. But yeah, it's just a canonical test case. There's a lot of data.
When you talk about CFD, also especially turbulence, there's a term coming up called closing terms, or the closure problem per se. Could you quickly explain what that means? Because you have predicted this closure terms by a machine learning model, which is very, very interesting. But before we jump into the combination, how you predicted it and how the approach looked like, maybe you can first explain what the closure.
So I'll go back to what I was mentioning before when you asked me what turbulence is. And I say, okay, if you take this measurement of a system and you kind of track it, and then you will see that it's just going everywhere, maybe. So if you do it in time, you will see that when the fluid evolves, if you look at that position in your domain, the velocity will just fluctuate. Okay? So you can take an average of your measurement of your signal, if this is a time signal, and then say that measurement you took is just a superposition of an average quantity, this is your average during time, and a fluctuating quantity. Okay? And you can do this in time, and you can do this in space, and you can do this in space, but in a single direction. This is what I did. So I took the average in that homogeneous direction, and then I have my closing term, which are the fluctuations. So that original signal is made up of an average part and a fluctuating part. And if you apply this decomposition to the Navier-Stokes equations, there's a term that come up that is just the fluctuating quantities. These fluctuating quantities are what, in addition to your average quantities, recover kind of your original flow. So, but the problem is like these add an additional variable to the system, and then the system becomes enclosed. So you need to find a model so you can add a new equation to the system that then you can solve the system of equations. This is what these are called, the closure terms. And this is done in Turbulence. It's done for, as I said, for time averages simulation for runs, for spatial filter simulations, LES. And then I also did it for my simulation with the span-wise average, this homogeneous average direction, Navier-Stokes. We also have closure terms. All of them have different meanings, but kind of the underlying theory is the same.
Yeah. How did you then approach this issue with a machine learning model? Was this the bottleneck you were talking about earlier on, where you got a bit frustrated? And how did you approach it? Yes. How did you get around this problem?
Yeah. Okay. So I was frustrated. I didn't know. So we're trying to do it from a physical point of view, but our equations, the span-wise average Navier-Stokes equations, we just average a whole direction, but the whole of it, not small parts like LES. It's not spatially filtered. It's like span-wise average, is the whole direction. Mm-hmm. They bring up these new closure terms that makes your mid-flow quantities, like the average velocity and pressure, behave very different from runs or LES closure terms. Like these closure terms are actually providing a different attractor, a different way of the fluid to evolve in time that in other simulations. So we need to model this. Mm-hmm. And if we just take models from runs or from LES, they wouldn't work because these are actually models that are aimed at a different type of conceptual average, mm-hmm. as I was mentioning. So we kind of were just left with nothing. Like we had to derive either a physical model from scratch, or to do a data-driven model. So we tried some physical models, I guess, that were kind of similar to these other models from runs and LES, more focused on span-wise average Navier-Stokes, but they was not working at all. I was kind of feeling a bit frustrated at that point. And then it's like, okay, I can just run a 3D simulation. I can compute what these closure terms, these fluctuations should look like, and I can make a model learn how to predict this fluctuation when I just input to the model a known quantity, my span-wise average velocity. So I'm just trying to feed this data set of known quantities, the mean flow quantities, and the closure terms, the fluctuating quantities. I just try to a model that can map from one to another. Mm-hmm. And this is like this was kind of my last resource. I cannot really derive a physical model for you. I will just try to make this data set fit into a machine learning model, so model that can be tunable, that you can just do optimization through it, and it will hopefully learn how to do this mapping from one to other.
Yeah, so neural networks in general are like very nonlinear equations at the end of the day, right? So did you use any kind of special neural network for this approach, or was it like specifically designed for this problem?
It was a bit of both, I guess. So we were doing kind of full flow field prediction. So where the output of my model was the full closure term, like the full domain of your cylinder and everything. Mm-hmm. How the closure term looks like, okay? So to do that, I mean, you can do it like, let's say, point by point, but that's quite expensive, even if it's a 2D simulation. Or we could do, for example, convolutional approaches where in the end you can just have the whole picture. So you just input like, let's say, image type data. Mm-hmm. So it was a 2D data. So like gray image with pixels from 0 to 1. And then you output your closure terms, which is also, let's say, image type data, gray data. So it's the same. Mm-hmm. And this was fitting my needs. But there's also some important properties that convolutions have. For example, they have the translation invariance. Mm-hmm. And this means that if they learn some pattern somewhere in your flow field, they will be able to recognize it somewhere else. Like if you shift that kernel, that filter, it will be able to identify those structures somewhere else. And that's something very important in any turbulent model. And there was an additional benefit, and it's that this was very specific to our simulation, like to our solver. So we were using like Cartesian grid methods, like inverse boundary methods. And the nice thing about this is like your grid is not fitting the geometry that you input. So my grid was just, let's say, a Cartesian grid, right? Yeah. Very simple. Mm-hmm. And then you take into account the effect of the boundary in your flow field for additional terms or whatever. There are many different methods. But in the end, your grid, which is how you save your data, is just Cartesian grid. So I could just directly get that from my solver, that grid, and plug it into my machine learning model. I didn't need to do any interpolation and other stuff you would need to do for example, if you have an instructor fitting mesh, then you will need to interpolate that to a Cartesian grid, and then that you can now input, like you can read it through your convolutional neural network, and then you need to interpolate back to your grid. So there's also some additional errors here, and we were just keeping those. But this is like very particular to our case because we were using this type of solver. But well, yeah, I guess there are other approaches, obviously, if you don't have this solver, but it just was fitting our case.
Yeah, this is kind of funny and also very interesting because you mentioned this right now, because you mentioned this like in a few sentences, but I assume the few sentences that you have just talked about took you a long time to figure out how to get to this endpoint. So what I would be interested in also, and I think the audience as well, is how did you even delve with only a CFD background and a little bit of programming, obviously, into the machine learning domain? Was it just you had to look at pure documentations, maybe had to look at TensorFlow documentation, and then just delve into it? Or how did you personally approach this machine learning journey?
Yeah, I mean, you're right. I had no idea almost on data-driven method before I started doing this. Really, I just kind of had to learn it because I knew that my only way to get my PhD was probably to just learn about this, because I was feeling very frustrated about the physical models. Mm-hmm. So I just start browsing the internet and so on and so forth. But then there are some nice, I guess, resources which are open online. One is like the Deep Learning book by Ian Goodfellow. That's a very nice book. I think that was one of the first things I read. And then I started getting used to the terminology and all of this that was very unknown to me at the time through that book. And then a lot of I don't know, random articles online, a lot of Stack Exchange, like the different ones, like the data science, the Stack Overflow, whatever. And then obviously it helps if you have good programming skills, because I mean, you are gonna start struggling with the model itself and understanding how it works. Then you need to implement it. And if you have a good good abilities on programming, for example in Python, then it's just quite easy to, let's say, run a quick example that maybe you can find, as you said, in TensorFlow or other libraries of this sort, and then run it. And once if you have a model running, then it's like, okay, let's start tuning stuff, let's start adding layers, knowing what a layer is, and you get used to the terminology, you start putting it in your small model and start growing that model slowly. But yeah, I mean, like machine learning has been such a boom in the recent years that, well, this is good and bad in the sense that there's a ton of information online, right? You need to filter that information a lot to get the good one. But again, there's some like very classic now literature about this that maybe it's good to look at. So just the book, as I said, is an example, but there are some good books that you would get in any list of what deep learning books should I look at. So I guess.
Is there any specific resource you would recommend in terms of CFD plus machine learning?
Particular research? What do you mean exactly?
Or like research, or like maybe GitHub repositories that you think are very, very interesting, but you maybe didn't have time to play with them.
The thing about this model, like CFD plus machine learning, is that it's normally very case dependent. Like everyone wants to do, like, there are so many different fields now in CFD plus machine learning. Like, okay, the first question is, what do you want to do with machine learning?
Mm-hmm.
Like, why are you choosing machine learning? Have you tried something else? So, for example, there was a funny conversation I had with my supervisor in Southampton. He said, yeah, I just went to this conference, and in the machine learning session, there was this guy doing how to predict with machine learning, like flow past a circular cylinder, same as I was doing before, but just a 2D flow and at a very Reynolds number. It's like, why do you even need machine learning for? Like you have just two parameters you need to do. It's like an harmonic system, right? You don't really need thousands of trainable parameters to infer or whatever. Like it's just really two parameters that you can just know. So first question is like, what do you want to solve with machine learning? There's many different valid points that you can take here. Like I want to, I have a very coarse experimental measurement, and I want to make it look more in detail, like super resolution, right? Or I just want to accelerate my CFD simulation. Or I don't know, I want to do a turbulence model. I want to infer some training, some closure terms. So I don't know, there are many different repos that you can look at. Just first decide what you want to do machine learning for in CFD. And then I guess you can look at whatever repositories on GitHub.
Yeah, and I think to everyone listening right now, Bernat has also a Twitter account where he shares or likes or retweets a very interesting post. So if you're interested in fluid mechanics as well as machine learning or data-driven modeling, then make sure to follow Bernat. I will put a link to your Twitter profile down in the description, as well as to your paper. Is there anything else regarding the paper that we might have missed, some important aspects in terms of machine learning, data-driven modeling?
No, and in the end, it's just, we've covered everything. Like the important bit is like, when you cannot derive a physical model and you have the data available, then maybe you can do a data-driven method and then develop a model for it.
Mm-hmm.
And like neural networks are are universal functions approximators. So probably you can fit anything, like if you have the right data, but you need, I guess, to know what you want to obtain and how, and and ask yourself if it's worth it to implement one of these models, or maybe look at, there's already some physical model, that would work for my paper that, but actually that was pretty new and we couldn't find any. So yeah, we've covered pretty much everything, I guess.
Okay, very interesting. Before we wrap things up, Bernat, we had one question coming in on Twitter from @ChurchillMick. Maybe you know him.
Yeah. I read the question, I think.
Yeah, and he asked, in 10 years, what would you guess the role of machine learning in CFD will be? Integral part of production simulations, relegated to analysis tasks, machine learning used as holistic black box replacement, or targeted to, for example, numerical solver components? was kind of a long question, but maybe you.
Yeah. Okay, so there are different things. Okay, so first thing about machine learning as a field. I think we are now kind of reaching the climax of in research where people is using. I mean, this funny statistic, like funny thing I looked at. So you take Yann LeCun, one of the fathers of deep learning, and you look at his citations per year, okay, and you can see like it's kind of a Gaussian distribution. So it's like this bell that it looks like now we are reaching the top, really. So your second derivative of this graph is already negative. It's decreasing every year. Mm-hmm. The number of citations that he is getting respect to the previous year. So we are reaching that. And I think that this doesn't mean that in 10 years, deep learning will be obsolete. Not at all. It just means that maybe all this boom that we have experienced now would be kind of people will be just using it as more like as a, I don't know, known tool, same as people is using now, P.O.D. or DMD in fluid dynamics, like a known tool where you just want to learn whatever, research whatever. But it wouldn't be like the main focus of your work, just to derive a new machine learning model for turbulence closures. Maybe it will be, but probably not in that respect. I think it will have a lot of impact on data analysis. So now we are in these times where exascale computing will start become a reality. We'll have exascale computers. So the amount of data that will be generated, it's like super large. And if you want to do like post-processing analysis on this, you will need tools that are capable of doing this. And machine learning can definitely have a big impact on this area. So I think this will be one of the fields where machine learning will be more prominent in the future. And then again, he's right that maybe using it as a part of a CFD solver will also be important. So I just recently read this paper by Kochkov, it was, and Brenner in PNAS. It's like machine learning accelerated CFD. So they basically take an initial flow field, like a very well-resolved flow field, then they interpolate it to a coarser grid. They perform the time-step operations you need to do, compute your convective term, diffusive term, add them up, whatever. And then you have your next time step in the coarse grid that you can re-approximate very well into your finer grid. And you do that by your machine learning model learning how to do the interpolation of the operator, your divergence operator, your gradients, and so on. You kind of learn how to model those that you would have in fine scales, but doing it in a coarse grid. And then you can run this simulation in coarse grid, but still obtain very accurate result. So it's like a compensation for the coarse grid poor resolution, like poor results that you get normally when you, for example, require DNS, but then you don't reach to do DNS, then you have a very coarse simulation, and then if you compare results to DNS, you are very far from them if you don't account some model for turbulence. So I think it can have an impact on accelerating CFD simulations, maybe in this sense, and definitely a lot of impact too on control. So in turbulence, for example, for your aircraft, you need to control your flaps, your slides, or for whatever pipes you can control, I don't know, the inlets and the outlets, and by plugging jets here and there like flow jets. So the control of this system is quite complex normally and very nonlinear. And machine learning has been done pretty well in this recently. So I think this will stick for a while too, like doing like fluid flow control through machine learning would be also an important field in the next 10 years, I guess.
Yeah, super interesting. And thanks for giving us this insight, Bernat. I really appreciate it. To wrap things up, is there any kind of advice you would give to the audience out there, maybe in terms of going into the field of CFD, not without machine learning or with machine learning, or even doing like a PhD? What would you tell them?
I mean, if you really like CFD and you really want to get into it, I guess doing a PhD is the way to do it, but not necessary 100%. Like everyone would have their own personal circumstances and so on. And I get a lot of very good insight during my MSc in CFD. I did like a lot of the knowledge, like it's like basic knowledge, but it's what you need, it's enough. Like obviously, if you do a PhD, it's like you specialize a lot in a single thing, and then you can look back at very basic stuff that are not super related to what you did. It's like, wow, this feels so far and still so basic, but I've not been focused on this for so long that I don't even remember almost. Mm-hmm. But yeah, obviously, I learned a lot during my PhD, and I'm very, glad I did it now. Maybe if you ask me during those periods of downs, I would say like, no, I don't know, I'm not so sure. But right now I would say, yeah, it's definitely worth doing if you like the lifestyle that I described, and then you take into account all the good and the bad parts we've talked about. Yeah.
Yeah. If I ask you now, would you do a PhD again? What would you say?
I guess I would say yes.
Yes, again.
Yeah, I guess, but it's just because of the time of, that you are asking me this question. You asked me this question maybe 2 years ago, maybe I said no.
Yeah, I see. Yeah, but
once done, it's done, Yeah.
Yeah, but would you see, like, now that you told us about the time in Singapore where you had like a broken knee and the hard time doing your PhD, would you think that in a few years, like in 10, 15 years, you look back and think that those hardest time were the most beautiful time in your life? Would you agree on that?
Yeah, no, definitely. Like, obviously, I've lived a lot of experience on these 4 years that I wouldn't have lived. Like, one of my reasons to choose to do a PhD, specifically this one, is just I could spend some time in Asia. I don't know. This was one of the motivations for me, not only CFD. Of course, I wanted to learn more about CFD. I wanted to get a PhD and so on, but it's a very long period in your life. And you need to take into account that if you focus only like on your profession, on your work for 4 years, then it's very highly probable that you will not feel good about it at some point and you will just drop it. So you need to kind of do more like a life plan, I guess, than just a professional plan.
Yeah. That's very, very good advice, Bernat. I thank you so much for being part of this show. It was very, very interesting to get some insights from a machine learning or CFD expert as well. I thank you so much, and hopefully there will be a second part in the future. Who knows?
Yeah, thank you very much for the invitation. I really like talking to you, and I'm enjoying all the other podcasts you're doing. So nice work and keep it up.
Thank you so much. See you next time.
Okay, see you.